Well, welcome back. We are going to continue today with a little bit more about trig limits. It's just a little bit of a leftover topic from the end of section 7.1 of my book. Then I'm going to go back to chapter 6. I'm going to spend quite a while on that. So what that's all about is differentiation, how to solve derivative problems. I'll show you a whole bunch of different types of problems, and we'll pay special attention to the product rule, the quotient rule, and the chain rule. And then after that, I'm going to do derivatives of trig functions, which is the rest of chapter 7 in 7.2. So that's the agenda for the 2 hours today. Of course, for those of you in the room, we'll continue with question and answers after that. So any questions before I dig in? Just wrap up that little bit from last time. Yeah. The quiz, which chapters? I am not 100% sure. I will have to, maybe I'll discuss that at the end of the 2 hours. We can work out exactly what it is. But I will be covering up to, as I said, yesterday's class. So it would seem like at least I will have covered everything. We can work that out by consensus. Okay, so without much further ado, I just feel like I should show you just a few more trig limits. I know this is going back a little bit, but I talked about how to deal with the small case. I would like to deal with trig limits, the large case, and we've already talked about it, so I don't have too much to say. But I just wanted to sort of mention, if you have a limit like this was the last of the 4 limits that we looked at. They all looked pretty similar. But I wrote that one up, and I didn't really say how to do it. Well, the answer is you do it with the sandwich principle. I'm not going to write it out again because we've looked plenty of times at it, but you basically start off with sine 5x is between minus 1 and 1, and then divide both sides by x and use the sandwich principle. Okay, so basically the idea is that when x is large, there's not much else you can do. We have this beautiful thing, sine of small looks like the same small. So if this was the limit as x goes to 0, sine 5x over 5x goes to 1 in the limit. But when it's large, there's no such nice relationship. This is about the best you can do for sine and cosine. So that's basically the moral of the story. So I'm just going to give you sort of one example from 7.1.3 of my book. It's just sort of an illustrative example. And then I don't really have much else to say about trig limits. I just didn't quite get time to finish this last time. So we're looking at a limit, and it's a polynomial on the top, but I've got this sine term that is 3000x to the 9. Sine of that quantity divided by 2x squared minus 1 minus cosine of 22x. Okay, so if it weren't for the trig things, that would look like a poly over a poly. And we know how to handle those. Well, my point is that the trig for large x, or for any x for that matter, this is between minus 1 and 1, and the same with the cosine term. So how much difference does it make? Not a lot. It just adds on to the constant. Instead of 5, you should think of this as between 4 and 6. Right, because I'm adding in a number between minus 1 and 1. So basically, I'm going to follow the same advice that I did as if it was just a poly over a poly. Take a big-ass fraction bar like this, because you're going to need a lot of room, and divide by the leading term. Well, the leading term is just 3x squared. And of course, I have to multiply by 3x squared to correct it. And then on the bottom, here the term is 2x squared, and of course the correction is 2x squared. This is not very well erased. It's as good as it gets. All right, so what do? We tidy it up a little bit, and we are going to dispense with this very quickly. 2 over 3x minus 5 over 3x squared. And then we have this term, which I can't really simplify, so I'll just leave it as it is. what is it, 3000x to the 9 all over 3x squared. And I do the same on the bottom. 1 minus 1 over 2x squared minus cosine 22x over 2x squared. And all that's left is to cancel out these x squareds here, and you have a 3/2. Well, now we have to work out what happens. We've been saying, oh, as x goes to infinity, that goes to 0, that goes to 0, that goes to 0. You just need to do a little bit of work on these terms. So in order to solve this properly, you'd have to do the individual sandwich principle on this, and you'd set aside a separate thing and show that limit is 0, and also you'd show this limit is 0, the cosine 22x over 2x squared. So you have to show using the sandwich principle on a separate sort of sidebar. And the solution's the same. You know, the sign of this quantity, even if it's outlandish, like 3000x to the 9, that's between minus 1 and 1, and then you divide by 3x squared. The top and the bottom go to 0. You do the same on the bottom. And so the conclusion is that this just goes to 1 plus 0 minus 0 plus 0 over 1 minus 0 minus 0. So we've got the 1s. Everything else just goes away. We still have the 3/2, and the answer is 3/2. So anyway, that's just a little bit of wrapping up of 7.1.3. Yeah, question? Okay, I'll just do one of them. You get to choose. Which one do you want, the cosine or the sine? Okay. So here's the argument, and I'm going to write it out pretty briefly. But you start off, see, this is a large value. X to the 9 is large. So just about the best thing you can do is to say that it's between minus 1 and 1. That's true for sine of anything. Now divide all this by x, what is it, 3x squared. And then you go minus 1 over 3x squared is less than or equal to the quantity we care about, sine 3000x to the 9 over 3x squared, which is less than 1 over 3x squared. Okay, now you have to write some sentences. The limit of this goes to 0 as x goes to infinity. The limit of this is 0 as x goes to infinity. This is, therefore, has the same limit, 0, by the sandwich principle. So you need to write out some descriptions, but I've done that in the past, and I've more or less just dictated what to write out. Okay, so that's how you do it, and you should repeat that for the cosine. That would get you the full points. Right? Just to say that it's 0 is not really good enough, although here I think you can just say that that's 0. Right? We know if there's an x on the bottom, it goes to 0. We didn't actually really prove that. You need the epsilons and deltas to do it, but that's the basic gist. There's also a section 7.1.4 about the other case, but I think that I don't have time to cover that, so I will just have to omit that. And there's a proof in 7.1.5 of the book of that sine x over x limit, but again, I will have to just assign that as a reading exercise if you're interested. Okay, so I want to move back to chapter 6. There's a big old chapter about how to solve problems using differentiation. So last time we looked at what the derivative actually is. Well, now let's look at some practical ways of calculating derivatives. And actually, ironically, we're going to start off with an impractical way of calculating derivatives, but we will soon move into practicalities. Okay, so that's the game plan for about the next hour and 20 minutes, and then the last half hour will be trig derivatives. We may not even need that long. Okay, so from a point of view of Math 103, that should bring us right up to speed and actually up to yesterday's class. And from the point of view of anyone else following along with the book, we will have finished up to the end of chapter 7. Okay, so that's the plan. So here we are in chapter 6, and the first thing I'd like to talk about is we've got this formula for the derivative. F prime x is the limit as h goes to 0. You could write delta x instead of h, but I'll just keep it as an h. F of x plus h minus f of x over h. So that's the definition of the derivative. Of course, if the limit doesn't exist, then the derivative is not defined at x. And you can actually use this to calculate certain derivatives. In fact, some of the time you might be asked to find a derivative using the definition. I'm just going to show you one example. If f of x happens to just be root x, suppose the question was using the definition of the derivative, i.e. no rules, you have to just do it using this formula, but they may not tell you the formula, they just say using the definition, find the derivative of f prime. So that's the question. Find f prime of x using the definition of the derivative. Okay, so basically what this means is we have to actually just invoke the formula, which I'll write up again for good measure, just to remind us that we actually need to produce it. But then I will replace the function f of x plus h becomes square root quantity x plus h, and f of x is root x. So how do we deal with this? Well, it's got a square roots in it that are pesky, so we multiply by the conjugate and then divide by it again. So in this case, we're going to multiply by root x plus h plus root x over root x plus h plus root x. And when we do that, we get a difference of squares on the top. It's always the limit as h goes to 0. X is just fixed. We're going to get x plus h minus x all over h square root x plus h plus square root x. Now the beautiful thing happens that on the top, the x's cancel out, leaving you merely with an h. But then the h's cancel out, leaving you with just a 1. So this algebraic expression, we haven't actually taken any limits yet, we've just done some algebra. It reduces to 1 over square root x plus h plus root x. Now we take the limit. And we can do this just by replacing h by 0. We're effectively using continuity here. And we get 1 over root x plus 0, just plus root x. See, we couldn't do this first because in any of the previous expressions before we cancel the h's, you get 0 over 0. Here, though, we do not get 0 over 0. In fact, we get 1 over 2 root x, right? Because it's root x plus root x on the bottom. So we've actually proved directly this formula. The derivative with respect to x of root x is 1 over 2 root x. And I would encourage you to learn that formula in that form. I know it's a special case of the x to the a rule that I'm going to mention in a few seconds, but whatever else you learn, this one with the square root of x comes up so often that it's a pain to change it to x to the half and x to the minus a half here. Just learn that formula. You will not regret it. It's not very hard, and it comes up all the time. Okay, anyway, this is a special case of a general rule which I'm not going to prove. You could find the proof actually in 6.1, but it turns out that d dx of x to the a is ax to the a minus 1, and that one, of course, you have to learn. This is true for any number a. Any real number a, that's true. Okay, so that's a fundamental sort of rule. As I say, there is a proof in 6.1, at least when a is a positive integer. But we have to wait till we do exponentials, which is coming up a little bit later, in order to get the general proof when a is not just an integer, but could be any real number at all. Nevertheless, it's true. I'm going to quote it, and I might as well comment that that agrees with what we just did over there. E.g., if a equals 1/2, you get d dx of x to the 1/2. You just drop the index out the front, 1/2, and then you subtract 1. So if you take a half minus 1, you get minus a half. And of course, another way of writing this, x to the minus a half, is 1 over root x. So of course we get the same formula. I'm just suggesting we don't waste our time too much with this. But if a happens to be equal to 2, well, d dx of x squared, you can just write down 2x, because it's actually 2x to the 1. Right? You put the 2 out the front, and you knock this power down by 1. How about something like this? d dx of x root x. Well, we're going to learn a product rule very shortly, but you don't need it here. The correct thing to do with such a thing, with such an object, is to write x root x as x to the 3 halves. Right? It's x to the 1 times x to the 1/2. You add the indices and you get x to the 3/2. Then you can just write down the answer. You put the power out the front and drop it by 1. Drop the exponent by 1. And you get 3/2 x to the half, which is otherwise known as 3/2 root x, if you want to write it like that. All right? So that's a really, really useful rule. But it is a rule. I didn't prove it. When I write down these derivatives, I'm not using that definition with a limit. And that's the beautiful thing about it. Once you have rules like this, you don't have to calculate limits. The whole goal of calculus is to try to avoid actually calculating anything other than what you have to. So, without much ado, I move on to section 6.2, and I actually don't propose to spend much time on the first part of it, which is how to deal with sums or differences, rather than just to give you an example. Suppose I want to find the derivative of 3x to the 5 minus 2x squared minus plus 7 over root x plus 2. Well, I told you how to do the individual pieces here. X to the 5 we know. What about 3x to the 5? Well, it's just a constant times this, and it turns out constants are very nice when it comes to derivatives. You can see that directly from the limit expression. So basically, without the 3, it would be 5x to the 4. So with the 3, it just gets multiplied by 3. So moving over here, what I'm trying to say is the derivative of x to the 5 is 5x to the 4. So we actually know that the derivative of 3x to the 5 is 3 times the derivative of x to the 5. 5x to the 4. And actually, you don't even need to go that far. You can just do 15x to the 4 directly. You see, what you do is you do 5 times 3 is 15, and then you drop the 5 down by 1 to get the 4, the power there. Okay? So, in fact, we can do this directly without much work at all. First, I'd just like to change the root x on the denominator here. So this is d dx of, I'm not going to calculate the derivative yet, I'm just going to say it's 3x to the 5 minus 2x squared. I'm going to write this as 7x to the minus 1/2 plus 2. All right, let's follow our rule. 5 times 3 is 15, and drop the index. 2 times 2 is 4. We'll keep the minus. So you may notice that I just broke up the derivative into 4 pieces. I didn't even tell you how to deal with sums and negatives. I've already just done the first 2 pieces. It turns out for sums and differences, the derivative just goes straight through and acts on every piece. The derivative's like sums. The derivative of the sum is the sum of the derivatives, right? If I take 2 functions and I know their derivatives, I make a new function by adding them together. The derivative will just be the sum of the derivatives. That's pretty nice. It's true for limits, and it's true for derivatives. So in this case, I need to multiply 7 by a minus 1/2. So actually, I'll just write down minus 7 over 2. And instead of x to the minus 1/2, I have to drop the index down, or the exponent down by 1. So I take minus 1/2 minus 1. I get minus 3/2. What about the derivative of 2? It's 0. 2 is just a constant. The derivative of a constant is 0. One way you can see this is it's just a line. So of course it has slope 0. Another way you can see it is that x to the 0 is 1. The derivative of x to the 0 is 0 x to the minus 1. So it's the derivative of 1, just the constant function 1, is 0. And of course if you multiply the constant function 1 by any other number, like 2, well, the derivative is still 0. It's multiplied by 2. Okay, so there's nothing difficult, really, with sums and differences. The difficulty comes when you try to do products. And this is where we need something called the product rule. And I'm going to spend a few minutes on the product rule and some time on the quotient rule. And actually, I'm going to do the chain rule after that so we get all the rules out of the way. In the Math 103 syllabus, the chain rule is a little bit later than the other 2 rules, but since I'm at this point and you've already done it, I don't see any reason to delay. So, let us spend a little bit of time on the product rule, the quotient rule, and the chain rule. First, I want to just see if anyone has any questions at this point. All right. Well, it's 6.2.3 in my book. It's called, well, it's about the product rule. Okay, so I told you if you add two functions together, you just add the derivatives. Not true for products. Just not true. It's easy to see. The derivative of x squared, well, you can think of x squared as x times x, but you can't just differentiate x and multiply the two together. Else you get 1 times 1. No good. So there is a more complicated rule, and it has, I'll give it to you in two versions. Version 2 is actually the more common rule, but it's a common way to write it, but it's worth learning this. If h of x is the product of f of x and g of x, so then the derivative, assuming these are both differentiable, the derivative is not just f prime times g prime. It is actually the derivative of f times g of x plus f times the derivative of g. So that's often how it's written. Sometimes, and perhaps even in my book, I forget this could be g prime times f, but of course products are commutative. Okay, so you sort of take the derivative of one times the other plus the first one times the derivative of the second. You never actually multiply the two derivatives together. The other version is if y happens to be equal to u times v, where these are implicitly understood to be functions of x, then dy dx is equal to v du dx plus u dv dx. Now, of course, you could write this as u dv dx plus v du dx, but I think it's better to learn it this way. And this is the most useful form of it, so I'll put a box around it. See, the reason I think it's better to learn it this way is that when we do the quotient rule, there'll be a minus there instead of a plus, as well as something on the denominator. And I think it's just easier to remember them in the same order. So v du dx, v is g of x after all, du dx is f prime, so of course this is the same as this, and u dv dx, well that's u, and that's dv dx. So actually these two formulas are just different ways of writing exactly the same thing. So the question is, how do you use the formula? Well, here's one simple example. So, if y is x cubed plus 2x outside of 3x plus root x plus 1, what is dy dx? Okay? So that would be a reasonable question. Now, it would be a legitimate technique to expand this whole thing out. You'll get 6 terms. You might be able to gather some of them. In fact, you will, I think, but, well, maybe not. But nevertheless, you'll get some number of terms, and then you can differentiate them. Now, when we do derivatives of trig functions, that won't always be possible. For example, x sine x is a product of two things, which you can't simplify. So, in this case, I would still recommend using the product rule because it will save you some messy algebra at the beginning. So let us let this be equal to u, and let this be v. So here's my working. U is the first term, x cubed plus 2x, and v is equal to the second term, 3x plus root x plus 1. Well, it turns out that dy dx, and I'm just going to write out that product rule, it's v du dx plus u dv dx. Well, we know what u is, we know what v is, we're going to need the derivatives. So actually, back over in our working, let's differentiate. X cubed, the 3 drops out the front, you get 3x squared. 2x, the derivative is just 2. It's a line of slope 2, or you can think of it as 2x to the 1. And when you differentiate, you get 2x to the 0, which of course is just 2. dv dx, 3, we don't have to change root x to the 1/2. We can just write it down using the formula that I proved earlier, 1 over 2 root x. See how nice it is to know that particular one? Comes up all the time. The derivative of 1 is 0 because it's a constant. So there it is. All I have to do is plug it in. V is 3x plus root x plus 1. Du dx is 3x squared plus 2. And I've run out of room, so I'll go down onto the next line. U is x cubed plus 2x. And dv dx is 3 plus 1 over 2 root x. And there is the derivative. A couple of comments. You might notice that I actually multiplied v by du dx and u by dv dx and then added those two quantities. So sometimes people put a little x there to remind themselves it's actually this times this plus this times this. And the other comment is that maybe we should be simplifying this and expanding it out. Well, you know, my philosophy there is if we really wanted to do that, we probably should have expanded the original thing first and then differentiated. So you have to let experience be your guide here. Normally, a question would say, do not simplify your answer, or do simplify your answer. If it's ambiguous, you probably should consider simplifying it. In this case, I don't know. As I say, if I really wanted to simplify this, I would have simplified that first and then differentiated. So that's a sort of simple case of the product rule. Sometimes there are actually 3 terms. It's worth learning a 3-term version of the product rule for when it comes up. So, suppose, 3 terms. If y happens to be equal to uvw, you see, you could just apply the product rule. You could think of this as uv times w, and then you find the derivative of the uv piece separately. It's a bit of a mess. It's actually better, I think, you're better off learning the 3-term version separately. So it's the same form, dy dx. The idea is we're going to differentiate one of them, du dx, and not the other two. Well, that takes care of u. But now we need u dv dx w. And finally, w needs its turn to be differentiated. W dx. So that's a useful thing to remember. Okay, so I have an example in the notes in section 6.2.3, but I'm not going to do an example of it. You just have to write down u, v, and w and write down all 3 derivatives. So you don't have a cross thing anymore, but you just have to keep track of your things. Of course, I will do an example on demand. If anyone here, even one person, requests an example of such a use of the formula. No one. Okay. So I, again, refer you to the book, and I press on. So that's pretty much what I have to say about the application of the product rule. Of course, you need to practice these things. Okay? For those of you in the room, for those of you watching on the web later or in Math 103, you know, the amount of homework that you get assigned or exercises, it's not enough for everyone. Okay? For some people, it's too much. For some people, you need more. If you don't feel like you completely understand it and you want to make an effort to understand it, seek out more problems. Do some of the other problems that weren't assigned for homework. Ask me. I'll come up with problems. Pick any 2 functions that you know how to differentiate and multiply them together. See if you can do it. See if you can use the product rule. Okay, these are tactics for doing well in this course. Anyway, I do want to say just a few words about why the product rule is true, just because it's kind of nice. So basically, without getting into too much detail, I do have a little bit of a justification of this in the book, actually, in 6.2.7. But what I want to do, let's see if I can be consistent with what I actually have got in the book. Right, so I want to presume I have a quantity u, and then I change u a little bit, so it becomes u plus delta u. Well, why do I change u? Because u depends on x, and I've changed x by some amount delta x, and that is going to create a change in u. V also depends in x, so if I change x a little bit, then V will also change by a little bit. Okay, so we are interested in what is the change in UV. How much does UV change when I change x? Well, if you look at it, UV starts off as this area, but the new UV is actually equal to U plus delta U times V plus delta V. So the new value is this area. See, this is UV. The new value is this entire area. So I started off with x, that gave me u, that gave me v, and uv is this area. I change x by a little bit, and u becomes u plus delta u. It changes a little bit. V becomes v plus delta v. It too changes, and we end up with this new value. So what's the difference? The difference is the new value minus the old value. So I'm going to shade in the difference with a sort of squiggly thing. Okay, that squiggle is the change. That's the change quantity. So what is that quantity? Well, we have three rectangles. This one is delta u, or the change in u, times v. And this one here is u times delta v. And then we have this tiny little one here, which is so small we're going to basically ignore it. And we have delta u times delta v. Right? It's a rectangle of width delta u and height delta v. Anyway, so basically the change in uv, well, the new is this, the old is this. So the change is equal to, well, what is it? It's v delta u plus u delta v plus delta u delta v. And I'm just going to sort of ignore this because it's really, really tiny. That's not much of a proof, but it's not far from a proof. And anyway, the point was just to motivate that you get a v times the change of u plus a u times the change of v. And that's basically the product rule. I'm leaving out some details. Where's the delta x? You actually have to divide by delta x and take limits to make this work. And there is actually in the limit your du dx and your dv dx, but that actually goes to 0. So it's just by way of motivation. I just want you to understand where these extra terms come from and why it isn't just the derivative. And I think the rectangle gives a nice little visual idea of that. All right, as I'm erasing this board, does anyone have any questions about the product rule? Go on with the quotient rule. If you have a question, start shouting it out. All right. Well, I don't really want to say too much about the quotient rule because actually it's just the product rule in disguise, as it were. So let's just say what it is. So in the book, I actually do two versions of it. I'm going to skip straight to version 2 because it's the most useful one. If y happens to be equal to u over v, then dy dx, it's the same as the product rule, v du dx, and you have a u dv dx, but instead of a sum, there's a minus in the middle. You also have one other thing, you have to divide by v squared. Seems a little bit weird, but that's how it is. Just to motivate where the v squared comes from, the derivative of 1 over x is minus 1 over x squared. You can work this out by writing 1 over x as x to the minus 1. So you're going to get minus 1x to the minus 2. But this is quite a useful thing anyway. Just as an aside, that formula comes up a lot. So remember that. Anyway, so you see there's a square on the bottom and a minus. And that's the true origin of this v squared of the bottom and the minus there. It's just more general. Okay, so there's the rule. You have to be able to use it. One example, and then I'll move on to the chain rule, which is a lot more interesting. If y equals 3x squared plus 1 over 2x to the 8 minus 7, what is dy dx? Well, I'll set up the same thing. I'm going to let u be the numerator and v be the denominator. I simply need du dx, and I need dv dx, and I just follow my standard rules. Multiply by the exponent, and knock it down by 1. Constants go away. So dy dx is v du dx minus u dv dx over v squared. So it's a cross multiplication again, but you've got to make sure you get the order right this time. It's 2x to the 8 minus 7. V du dx is 6x minus u times dv dx. And don't forget to divide by v squared. Maybe this one should be simplified a little bit, actually. Well, what do we get? We get 12x to the 9. We're going to subtract 42x, but then we'll have an extra minus 48x to the 9 and an x to the 7. So this should probably be simplified a little bit. I'm going to leave the details to you, since it's just straightforward algebra. Okay, so, but I don't think you can't factor anything nicely at the end there. There's no quotient rule for 3 things, because you can't really, if you had u over v over w, you'd just write that as u over vw. Well, it depends which fraction bar was bigger. So, that's pretty much the situation, except for one other type of operation of combining functions. And that one is the tricky one, composition. Right? We need to talk about how to differentiate the composition of 2 functions. So, I'm going to move on to section 6.2.5, which is the chain rule. And there are 2 versions of this that I'd like to tell you what they are, and then we'll look at some examples. So version 1, and here I really recommend you learn both versions. And I'll give you an example of where you need the first version fairly soon. Here it is. If h of x, it's not the sum, the difference, the product, the quotient, it's the composition. If h of x is f of g of x. Okay? Another way of writing this is i.e. h is f o g. It's not fog, it's just f little o g, f composed g. So if h of x happens to be equal to f of g of x, then the derivative, well, what should it be? H is f of something, so the derivative of h should be the derivative of f of the same something. But we've got to worry about g as well, and it turns out that you simply multiply by the derivative of that something. So it's not just f of x, it's f of g of x, so the derivative is the derivative of f prime g of x, but then you have to multiply by g prime of x. And that is well worth remembering. Version 2 of this, which also is worth remembering, is if y is a function of u, and u is a function of x, then dy dx is dy du times du dx. And that looks completely different from the first one. And yet, they are the same formula in disguise. Okay, so I have a few comments to make about these formulas before I start proving or doing questions. solving some problems based on it. So the idea is that y is a function of u, and u is a function of x. So y, of course, is a function of x as well, right? We take x, we change it, u will change. Not you personally, u, the letter, function. Then, since y depends on u, when u changes as a response to x, then y also changes. So ultimately, y is a function of x, but it goes through u. It's a sort of chain between y and x through u, hence the word chain rule. So this says the derivative of y with respect to x is actually the derivative of y with respect to u times the derivative of u with respect to x. These are not fractions. A derivative is not a fraction. It's a limit of a fraction, right? I mean, it's a limit of f of x plus h minus f of x over h, but it is not a fraction. So you cannot just say, oh, well, that's obvious. We could just cancel the du's, because there's no such thing as du. There's only du dx, dy du, as far as we're concerned. So basically, the beauty of this notation written as a fraction is that the chain rule says, well, you know, they're not really fractions, but you can cancel out in many circumstances as if they were fractions. Very, very nice. Now, why is this the same thing as this? Well, if y happens to be a function of u, you can think of this as saying that y is equal to f of u, and u is a function of x, say g of x. And if you do this, then, of course, f of u is the same as f of g of x, and that actually sends you back to version 1. So if you believe this, then you can get back to version 1. You see dy du is equal to f prime of u. But u is just g of x. So you get f prime of g of x. And of course, du dx is just g prime of x. So if you multiply dy du by du dx, you get f prime of g of x times g prime of x. And so that formula immediately becomes this formula. Okay, they look different, but they're the same. Now, without worrying for a second about why these things are true, let's just look at some examples. So, here's a nice example. Suppose h of x equals x squared plus 1 to the 99. Find h prime of x. Okay, I'm trying to angle for using version 1 here. You see, you'd be nuts to multiply this out. You'd be absolutely cuckoo to take x squared plus 1 to the 99. I mean, you get 100 terms in the darn thing. So you don't do that. Instead, you recognize that this is the composition of, first of all, you take your x, and the first thing you do is x squared plus 1. And then you take that and raise it to the 99th power. So it is a genuine composition. In fact, what you really want to do is let the inside function here be g of x, so that let g of x be the first thing you do, x squared plus 1, and you let f of x be the thing you do to this, namely take it to the 99th power. Then h of x is indeed equal to f of g of x. First, you take x squared plus 1, that's the action of g. Then you raise that to the 99th power. So it's a composition. So according to the formula, h prime of x is f prime of g of x times g prime of x. Well, we're going to need these quantities. If f of x is x to the 99, we know f prime of x is equal to 99x to the 98. Well, if you look at this, f prime of x is 99x to the 98. So this has got to be 99g of x to the 98 times the derivative g prime of x. And now we can take our g. So that takes care of f. We take our g, which is x squared plus 1. So it's x squared plus 1 quantity to the power 98. And now we need to multiply by the derivative of g, which we can just see as 2x. So you get 99 x squared plus 1 to the power 98 times 2x. And we can consolidate the 2 and write that as 198x, x squared plus 198 power. Okay, so here's a way I like to look at this. I could actually almost write down the answer straight away. I have h of x is something to the power 99. What's the derivative of something to the 99? Well, it's like 99, that's something to the power 98, which is this. The only correction you have to make is that the something is not just anything. You need to multiply by the derivative of that something. Right? So the quantity, it's like 99 anything to the 98, and then you multiply by the derivative of that something. It sort of spits out its own derivative, as it were. All right, so that's an example of using that notation. I will do another example in due course. An easy little formula. You mean not in symbols, because I've just written 2 formulas in symbols, of course. Yeah, see, the difficulty of the quick way is it's nothing more than the other way, but done in your head. And it's quite hard to do it in generality. But if I had to do it, in generality, it would look something like this. If you just have a formula for d dx of something happens to be equal to triangle, okay, I'm reduced, since I've already done it using algebra, I now have to be reduced to boxes. But if I know that d dx of this is the triangle, then d dx of something or other is equal to the triangle, but with x replaced by this, times the derivative of this squiggly thing inside. Okay? So that's my hieroglyphic version of this whole thing, right? So if the derivative of x to the 99, if I happen to know this, is 99x to the 98. So I've got 2 functions, the square and the triangle. Then d dx of, say, quantity x squared plus 1 to the 99. Well, I just take that derivative template, but instead of x, I replace it by x squared plus 1, and then I need to multiply by the derivative of the x squared plus 1. So if this was x cubed plus 1, everything would look the same. This would be x cubed, this would be x cubed, but instead of multiplying by 2x, I multiply by 3x squared, which is the derivative of the x cubed. So that's sort of the quick way. Let's just see how to do the same example using u and v. So if, e.g., if y is equal to the same quantity, x squared plus 1 to the power 99, here's another way of doing the problem. Find dy dx. Let u equal x squared plus 1. If you do that, then y is equal to u to the power 99. Right? I mean, if u is this interior part, x squared plus 1, then y is clearly u, x squared plus 1, to the power 99. So now we can use the formula. Well, I'll write out the formula first. dy dx is dy du dx. So we're going to need to know du dx. Well, we just differentiate x squared plus 1 to get 2x. dy du is 99u to the 98. So, of course, this product, dy du, is 99u to the 98. du dx is 2x. And you might think that's the answer, except that you're not allowed to just leave that u there. You need to resubstitute back for u in terms of x. And we know u is equal to x squared plus 1. So, of course, we end up with our same answer, 198x, x squared plus 1 to the power 98. All right, so that's the same problem done in a whole bunch of different ways. Now, might as well give one other example, e.g., if y is equal to square root x cubed plus minus 7x, what is dy dx? Well, I let the inside bit be u. Let u equal x cubed minus 7x. Then y is equal to root u. I need du dx, so I just write it down. It's 3x squared minus 7. Easy enough to read. And dy du, I know the derivative of root x is 1 over 2 root x. So dy du is 1 over 2 root u. Great. So the formula says dy dx is dy du dx. Dy du, according to what I just wrote down, is 1 over 2 root u. Du dx is 3x squared minus 7. And I'm not going to leave the answer like this. I need to replace u back again by x cubed minus 7x. So I get 3x squared minus 7 over 2 square root of u, x cubed minus 7x. And there's the derivative. Okay, in terms of the hieroglyphic method, here's what I would actually, here's another way of doing it, just more or less in your head. It is more risky, because if you get it wrong without any working, then no grader is going to say, oh, sure, they knew what they were doing. At least if you have working, you could get partial credit. But if you determine not to do it, look, the derivative of the square root of something I know is 1 over 2 the square root of that something, right? So there it is, 1 over 2 square root, the original quantity. But then I need to multiply by the derivative of what we took the square root of, which is 3x squared minus 7. So you can see that it's right once you get used to the chain rule. Okay? So, I'll give you one more example. And it's a little bit of an exotic one. I've seen these things come up on Princeton exams all the time. And it really tests your understanding of the chain rule. So, here you go. I'm going to give you a function h and a function g. I'm not going to tell you much about them. All I'm going to tell you is h of x is equal to the square root of g of x. That I'm going to give you, there's some function g, and h is the square root of g. I'm not going to tell you very much about g, other than I'll tell you g of 5, bless you, is 4. And g prime of 5 is 7. So I'm giving you the value of g at 5 only. That's all we know about it. And I'm giving you the value of the slope of g, the derivative, at 5. I'm telling you absolutely nothing else about g. The question is, what is the value of h prime 5? Question mark. This is a bit different, but nevertheless still a chain rule problem, because h is the composition of the square root with g. Okay? So you're going to need to use version 1, pretty much. You don't absolutely have to. You could let this be y, and you could let this be, well, you could let this be u and all that sort of stuff. But the correct way to do this, I think, in my mind, is to say, let f of x be the square root of x. See, that's the missing function, but it's really there in disguise. So then, h of x is actually equal to f of g of x. You see, you take g of x, and then you hit it with f, and that makes a square root. So h of x is f of g of x. So we actually have our version 1 that tells us the derivative h prime of x is equal to the derivative of f at g of x times the derivative of g. That's the formula that I wrote up before. Now, we don't know much about g, but we know exactly what f is. We know f of x is root x. So because of this, we can immediately write down the derivative f prime of x is 1 over 2 root x. That's in my working column. So, when I deal with f prime of g of x, I have to take this formula, but instead of x, I have to put g of x. So if you look at it, you get 1 over 2 square root g of x. That's f prime of g of x. And I need to multiply by g prime of x. to run out of room. I need to do some erasing in order to finish the problem. Anyway, just stare at that for a few seconds. It's sort of weird. It's not like stuff you normally see. So these questions, I have to tell you, from previous experience, at least in Math 103 exams, when these questions come up, they are invariably done quite poorly. Mostly because I suspect version 1 of the chain rule with the F's and G's is neglected. Everyone knows version 2 because it's so much cleaner. It doesn't involve all this F prime of G times G. It's just a nicer formula. But, nevertheless, here we are. I have a general formula for H prime of X. The question asks me what is H prime of 5. So I'm going to take my formula. I'll just rewrite this for clarity here. It's 1 over 2 square root G of X times G prime of X. And therefore H prime of 5, which is what we want, is 1 over 2 root G of 5 times G prime of 5. And so you see, it really helps that I know the value of G of 5, as given in the question, was 4, and the value of G prime of 5 was 7, and so this works out quite easily to be 7/4. Okay, that is very hard to do with version 2. You really get sort of, it's doable, but version 1 is the way to do it. So I have some more examples of this sort of question, or at least one more example in the notes, or in the book. How am I going for time here? Oh, I'm pleasantly on schedule. Don't get used to that. It doesn't happen very often. Good. I still have, of course, a whole bunch more problems to do. Now, we've got product rule, we've got a quotient rule, we've got a chain rule. I just want you to be aware, and this would take me a long time to do this example, but I just want you to be aware that if you had something nasty like this, I'm just going to write this out. I'm not even going to bother reading it because it's so messy. The point is, I want you to be aware that it's conceivable you could get a really nasty function like this that involves products and compositions and quotients. There it is. There's y, a function of x. You may have to differentiate such a thing. That's a fair game question. Find the derivative of this. How would you even attack that? I mean, the gory details are in the book. But in order to, and it's actually in section 6.2.6, which I think you'll agree is appropriately entitled a nasty example. So how would you do it? Well, the way to do it is just to break it down into many different things. Ultimately, what is y? What's the last thing that you do? If you look at it, what does it look like? Well, it looks like a quotient. It's something over something. So the first thing I do is let u be 3x to the 7 plus x to the 4th times all this stuff under the square root, which I'll write out really quickly. And let v equal 6x squared minus 4. So, of course, we know exactly what dy dx is. It's v du dx minus u dv dx over v squared. And what you should do is you should realize, well, we know v. We don't know du dx. We know u. And dv dx is really easy. It's 12x. And so is v squared. It's just that quantity squared. So you can actually put everything into this formula already. 6x squared minus 4 times something, and we'd better leave quite a lot of room for that something, minus u, oh hell, I don't really want to write this out again, but you're going to have to, so I guess I might as well, blah, I'll let you fill in that, times dv dx. This is where you need a wide blackboard, or lots of a wide paper, all over v squared. Now, here's the thing. We still need to find du dx. But we know what u is, and it's no longer a quotient. In fact, it's a sum. It's going to be 21x to the 6th plus, but now we need the derivative. And so basically the way I'm thinking of it is I'm going to use lots of paper. I'm just going to spread everything out, and I'm just going to sort of work my way in and see what I need. You see, what I want to do is then say, oh, hell, I should have called this something. But you see, it's a product of two things. It's x to the 4th times this square root. So I'm going to call the x to the 4th something like r, and I'm going to call the square root s. And then I'm going to use the product rule to find the derivative of this. And so on and so on. Now, I could spend a little time and do it. I kind of want to move on to other sort of things. I just want to make one comment. If I actually try to fill in this, I'm going to have r equals x to the 4th. I'm going to have s is the square root. And I kind of want to worry about the product. So what's dx of the product, rs? Well, you know v du dx plus u dv dx, but there's no u's and there's no v's. It's r and s. So you have to be very good at changing variables. It's s dr dx plus r ds dx. So I've just swapped the variables. It's not even a change of variables. I've just relabeled them. So, of course, we know dr dx, but to do ds dx, you have to use the chain rule, because it's the square root of something. So I kind of left all these pieces dangling, but I would like you to try to do this problem. I would like you, after the class, sometime soon, to try to do this problem, fill in all the details, and look in the book in section 6.2.6. That's my book, not the textbook. And see and check your answer against it. It's a good exercise. And if you can do something that tough, and it's not really hard, but it's convoluted, and you need to keep track of what you were doing and then reverse your steps. You see, once you find all the derivatives, you come back and you fill in the blanks to get the final answer. So that's why I want you to leave lots of room, separate the areas of the page that you're working on. If you can do something this messy, you can do any derivative in this course. That's basically what it comes down to. Okay? But you have to practice the nasty stuff. And then if you can do the nasty stuff, you can do the easy stuff. Okay? So, that's the end of 6.2 and all of its gory details. Well, I guess I should say a few words about why the chain rule is true, since it's actually one of the most important things in the whole course. So, I don't want to say too much about it. Suppose, though, well, maybe I'll do it over here. Suppose y is some function of u, and u is a function of x. What I want to do is I want to change x by a little bit and see what happens to y. That's what dy dx is, right? It's the ratio of how much the change in x affects the change in y. dy dx, change in y, tiny change in y for tiny change of x. So suppose I change x by a little bit. Well, last week I said something like du dx is basically approximately equal to an actual change in u over an actual change in x. So that means if I change x a little bit, I actually change u by approximately this ratio times the change in x. So in other words, this, of course, is g prime of x. G prime of x is du dx, and that's approximately equal to delta u over delta x. So if I rearrange this, this says that delta u is approximately g prime of x times delta x. So in the words that I used last week, this is the sort of magnification factor or the scale factor that I need to multiply the change of x by to get the change of u. If you were here last time, or if you watched last time, I was talking about things like this. I was saying, like, what's 6.01 squared, approximately? And we decided that because the derivative of x squared is 2x, when x equals 6, that magic number, the multiplier, is 12. So if you look back at it, or remember back to last time, I said you just multiply the change by 12 and you get the approximate change in u. Anyway, the point is, we want to see what happens to y when we change x? Well, according to this, we have, by the same equation, the change in y is approximately f prime of u times the change in u. Okay, so that's the symmetric equation. We change x a little bit, the response u changes by g prime of x times as much. But if we were to change u a little bit, then y changes by f prime of u times as much. Well, guess what? If you magnify something twice, what you get is the product of the magnifications. Okay, imagine a stick of chewing gum that you've already chewed. So you took it out of your mouth. A bit gross, but whatever. If I stretch it out by a factor of 2, and then I stretch that out by a factor of 3, you will have 6 times the stretch. So here, g prime of x is the first stretch, f prime of u is the second stretch. So, of course, actually this is all approximate. So this is f prime of u. The stretch in u is g prime of x. And there it is. The stretch in y is f prime of u, g prime of x, delta x, approximately. And of course, u is g of x. So that is not quite a proof of the chain rule version 1, but it's bloody close. It's almost there. Anyway, that's a sort of motivation for where this comes from. You don't need to know that proof. You do need to be able to do nasty examples, but I just want you to understand that the chain rule is nothing more than the product of 2 magnifications and a limit. These approximations become perfect in the limit, and that's all that remains of the proof, really, is to take the limit. If you're actually looking at the complete book of the Calculus Lifesaver, the proof is in the appendix, Appendix A. All right. Any questions about the chain rule before I move on to some other types of differentiation problems? If you have one, please start saying it and I will listen. No, if it's product, i.e. multiplied, you've got to use the product rule. The chain rule is for composition of functions. It's when you do something to x and then you do something to that. Right? So the product rule, if it's just a product of 2 polynomials, use the product rule. I did an example of that earlier. I don't think you were here, but yeah, another question. That's a good point. Yes, before I move on, I should really do an example of the chain rule of 3 things. I wonder if I had such an example planned. No, I did not. I will be happy to make one up, or if you have one, okay, well, I'll just make one up. Suppose that you would like to do, say, you know what? I'm going to postpone this for just a short period of time because I'm going to actually do trig derivatives, and there I have a better sort of, I'll do an example in terms of that. I might write myself a note. Chain rule, 3 things, and I will get onto the trig derivatives later. Okay? Well, I was just saying if you have, so the composition of functions is the difference. So the product, to evaluate the product, what you do is you find the first function, you find the second function, and you multiply. Whereas the composition is a different idea. You do something to the variable x, and you get the result. And then you take that result and you do the other function to the result. It's a different idea from the product. Well, here's an example. Suppose I take sine x, that's one function. F of x, g of x is just x squared. Okay? What's the product? F of x times g of x. Well, it's just x squared times sine x. It's 2 different functions. I just took the result of each one of them and I multiplied the answer together. No, that's the product. Here's the composition. Suppose I do f of g of x. Well, that means that's the composition of f and g. Right? That means I do g of x first to get x squared, and then I take sine of it. So another way of looking at it is you could do f of g of x is x squared. So of course this is sine of x squared. Okay, that's a different function from the product. And it's also a different function from g of f of x, which is g of sine x, which is sine x all squared. Another way of writing this, of course, is sine squared x. So it matters which order you do the composition. They're different functions. But it does not matter which order you do the product. F times g is the same as g times f. Okay? So look at the difference between this. This is, I just worked out x squared separately. I worked out sine x, and I multiplied it. Here, I have to work out x squared first, and then I take the sine of that. Whereas here, I take the sine of it, and then I square it. Right? So that's the difference. So for these two, you want to use the chain rule to differentiate them, whereas this one, you want to use the product rule. And you need to be able to tell that just by looking at the functions. It's a skill, and it takes some practice. Okay? Good questions. So I will come back to your three-way chain rule and say something about that then. Now, very quickly, I need to tell you one particular type of problem that comes up all the time, but, you know, no one ever says anything about it. This only takes half a page in my book, something like that, but it's really important. Here is the type of problem I'm concerned about. Okay? Suppose f of x is equal to x cubed minus 7 to the 50. There's a nice function. And consider the graph y equals f of x. Okay? I graph the darn thing. What I want is, what is the equation of the tangent line at x equals 2? What is the equation of the tangent line to that graph, which I haven't even drawn, but you know, you could draw it and there'd be an equation line above x equals 2. And there'd be a tangent line and I want the equation of it. Okay, how do you find the equation of a line? There's two things you need to know. You need to know its slope and you need to know a point that it goes through. Okay, just don't forget this. For these problems, you need a slope, which is a derivative, and you need a point, which is actually just a straight substitution. So let's do these things one at a time. We're going to need dy dx. Right, y equals this quantity here, which is f of x. So let's just use the chain rule. U is x cubed minus 7, and then y is equal to u to the 50. Right? So this is clearly a composition. We're not multiplying x to the 50 by x cubed minus 7. We're just taking x cubed minus 7, that quantity, and then raising this to the power of 50. So the best way to see this in my mind is that if u is this inside part, x cubed minus 7, then y is that quantity u to the 50. There's a composition. So du dx is 3x squared, and dy du is 50u to the power of 49. So according to the chain rule formula, dy dx is dy du, du dx. dy du is 50u to the 49. du dx is 3x squared. But we can't just leave that u around. We need to replace it back by x cubed minus 7. So this is 50x cubed minus 7 to the power of 49 times 3x squared, which I might as well tidy up to be 150x squared, x cubed minus 7 to the power of 49. Okay, now I have just found the general derivative y in terms of x. But I do not, that's not what the question is. I need this, but I haven't finished the question. The question says, what is the equation of the tangent when x is 2? And first of all, I want to find its slope. So I need the slope, I basically need the derivative when x equals 2. Not just for any x. This tells me the slope everywhere on the curve. Anywhere. You choose the x, I'll give you the slope. Well, I choose x equals 2 because that's what the problem said. So here's what I would write. When x equals 2, dy dx equals And I take this previous expression and I plug in 2. So I get 150 times 2 squared times 2 cubed minus 7 to the 49. Mercifully, 2 cubed minus 7 is 8 minus 7, which is 1. 1 to the 49 is just 1. So it's 150 times 4, which is 600. So that's the slope. Well, you know, the slope is a lot, but it's not the answer. We still need the equation of the tangent. So I said you need to find two things, a point and the slope. Well, we found the slope. How about a point? Well, we know x equals 2. What's the y value? We need to go back to the original equation. Y is equal to x cubed minus 7 to the 50. And you just need to notice that when x equals 2, y equals 2 cubed minus 7 to the 50, which is just 1. So we actually, or we could have done this right at the beginning. We didn't need the derivative to find this. Anyway, the point is that the line that we're looking for, tangent line, has slope 600, that's the derivative, and goes through the point 2, 1, right? Because when x equals 2, y equals 1. And so we can just use the point slope form, y minus that y coordinate 1 equals the slope 600 times x minus the x coordinate 2. So the equation, you should write, equation is that. And you could simplify this, I believe, if I'm not mistaken, to y is 600x minus 1199. Yes. Okay, so it's just finding the derivative, but you need to plug in the x value into both the derivative, dy dx, and to y to find the slope and the point, and then you need to use the point slope form. That is how you find the equation of a tangent line. Okay, if it just says what's the derivative, fine. But what is the tangent line, you have to do that extra work. Okay. Any questions about that as I'm erasing the board? Shout them out. You know the drill. Whoa! What was that? What was that? Oh, the board broke. No one saw me do that, right? It's not on video or anything. Okay. Well, I guess it won't go back up, huh? Nope. So, sorry? Those two are lit. I could use those two. Let's see how we go with these three. Those are sort of quite far out of the view. I didn't swear or anything, did I, when that happened? Well, you can apply a beep or bleep or whatever if I did. Anyway, lots of drama today. Yes, the rate of change of the board. Okay, never mind. So, let's see. After all this, I still have another board to break as well if I want to. Good. Let me move on to section 6.4 of the book, which is the topic of motion. This is not a physics class, but I need to spend a little bit of time, maybe 10, 15 minutes on motion, because after all, calculus was actually originally inspired by this little bit of physics. So I want you to remember the situation we were talking about last time. We have a one-dimensional axis, which could be horizontal, or it could be vertical. In fact, I'm going to spend quite a bit of time on vertical. I'm not considering motion in 2 dimensions, it's just 1 dimension. I just want to know where this particle is along a certain line and how fast it's going and what's its acceleration. So from what I said last time, if the position of the particle, of some particle, it could be a car or whatever, at time t, where t is in some units, if this is x, or actually x of t, if you want to make x a function of t explicitly instead of just sort of assuming that that's obvious, then its velocity at the same time is given by v equals dx dt. Nice ringtone. Okay, so v is dx dt. So there's the derivative. Now, that's actually what I wrote last time. I'm You know, I was talking about taking snapshots, photos, close time together. Well, we eventually came up with that formula. I didn't write it like dx dt. I wrote it as a limit and said, yes, it's a derivative, but that is the formula for velocity in terms of position. So you probably saw this in some physics class in high school, that if you actually had a graph of position versus time, then you could find the velocity, how fast the position was changing, by taking the slope of the tangent. And that's just the derivative. We ought to define the acceleration. Well, if the velocity is how fast your position is changing, the rate of change dx, change of position over time, well, then the acceleration is how fast your velocity is changing, right? So the acceleration is given by the symmetric sort of formula, a equals dv dt. So how fast is my velocity, my speed, if you like, changing? That's my acceleration, dv dt. So you might see that ddt, when you do a ddt, that tells you how fast something is changing. And when we do rates of change or related rates very soon, we will see a more general sort of case of that. When you differentiate with respect to time, it tells you how fast something is changing. Right? Calculus is all about change. We've done dy dx, right? You change x a little bit, y changes. Well, when time marches on, other things change. Right? The blackboard's condition, for example, has definitely changed. But it wasn't very differentiable, so let's not talk about it. Okay, so now, those are formulas. I could give you any function and say, oh, well, now calculate the velocity, calculate the acceleration. And that would be reasonable. But the most common examples that I really want to write, well, actually, before I do an example, I have something to add about the acceleration. See, dv dt, well, v is already the derivative of x with respect to time. So actually, dv dt, if you think about it, is the second derivative of position. Right? Because to find the v, you differentiate once. To find a, you differentiate that, which of course is the same as differentiating the original thing twice. So we already have an application for a second derivative. Did you know when you're driving the car and you step on the gas, you're accelerating, you're actually changing your second derivative of where you are? Bet you did not learn that in driver's ed. But you probably should have, because, you know, it's good to know how things work. Okay, anyway. I would like to really concentrate on one particular example, a very common type of movement, and that is constant negative acceleration. So let's concentrate on this special case, because it's an easy case to analyze. What do I mean by constant negative acceleration? I mean, really, gravity. Okay? That's some constant negative acceleration that we are unfortunately all subjected to unless we happen to be astronauts and go up into space where there is no such gravity. So basically, I think of upwards as positive. Well, guess what? If there's no force, if I just let this chalk go, which I'm not going to do because then it will break and I kind of want to use it, it will accelerate downwards. Now, that means it's getting faster and faster as it goes down. Now, sure, if I drop it off a tall building, eventually air resistance will come into play. And it doesn't just keep on getting faster and faster. Eventually, things suffer air resistance. But let's just not worry about that and worry about gravity, which will make things go faster and faster until they splat down on the ground. Okay, so what does such an equation look like? Well, what I'm trying to say is I'm taking a number line with positive being upwards, because I like to be positive when I look upwards. And I'm going to say that A, the acceleration, is minus g, where g is some constant number, which is acceleration due to gravity. And in meters and seconds, I should mention acceleration is meters per second, i.e. meters per second squared. Why is it meters per second? Well, velocity is meters per second, right? I'm going at this speed, 3 meters per second. How fast is your speed changing? That's your acceleration. Well, every second it changes by 5 meters per second. So it's 5 meters per second change every second. That's meters per second. That's a little ad hoc reason of why it's meters per second squared. So in meters per second squared, in meters and seconds, g happens to be approximately 9.8 meters per second squared. And I'll write it as m per s2. And 9.8 is pleasantly close to 10. So actually, a lot of the time, you will find problems will say, take g equals 10. Anyway, I am just going to tell you what the other two answers are. It turns out that v is equal to minus gt plus u, and x is minus a half gt squared plus ut plus h. And I have these two new variables, u and h. And I should say what they are. U is the initial speed, or initial velocity, really, i.e. at time t equals 0. Initial always means t equals 0. I always set my stopwatch to be at 0 at the beginning. And h is the initial position, or height, at t equals 0. I can no longer lift up this blackboard, so I will come over here. Okay, now I've just quoted these three formulas, and what I'm going to claim is that they are true. And I'm going to just do a sanity check. I'm going to check that they're true. It's not really a proof, and yet somehow it is a proof. Almost. Almost. If this is to work, I ought to be able to take dx dt. So this is a check. dx dt is what? Well, x is a half g minus a half g squared at gt squared. I better write this out again. X equals minus a half gt squared plus ut plus h. So I need to differentiate that with respect to t. The g is constant, so I get the 2 coming out there, and I'm going to get minus gt. The derivative of ut is just u. H is constant, so it goes away. And guess what? That is exactly the expression I wrote down for v. So the velocity is indeed the derivative of the acceleration. But of course, v is minus gt plus u, so dv dt is just minus g, because u is a constant, and that, of course, is the acceleration. So under these circumstances, I have shown you that my equations, which I'll just write up again, are at least consistent with each other. The derivative of x is v, the derivative of v is a, with respect to time. So I recommend that you learn these formulas, and then actually you don't need any calculus at all to use them. But you still need to be able to substitute and do clever things. So I'd like to give you an example, and this is in section 6.4.1 of the book. Here it is. There's the ground. I'm not quite 2 meters tall, but I guess if I extend my arm, I could probably make it. So I take a ball at height 2 meters, and I throw it up at a speed of 3 meters per second. So that's how fast it goes when it leaves my arm. So the ball goes up, and then it goes down. I'd like to know, how long does it take to reach the ground? I'd also know, how fast does it hit the ground? I'd like to know, how high does it go? If instead of throwing it up at 3 meters per second, I throw it down at 3 meters per second. If throw down at 3 meters per second instead, how long does it take now? You would think it doesn't take as long because it doesn't have to go up and then come back down. It'll just go straight down. And finally, then how fast does it hit the ground? Okay? So there's a suite of 5 questions, all based on the same or similar original scenarios. Well, let's do problems 1 to 3 first. In that case, we have u, the initial speed, is 3. I'll leave out the units till the end. And I have the initial height is 2. Right? Because I'm throwing it from 2 meters above the ground at 3 meters per second. So the equations become x is minus a half g t squared plus ut, well, u is 3, plus h is 2. And actually, I'm going to take g equals 10 for simplicity. So imagine that g is 10. So that would be given. Assume g equals 10. All right. So this is actually minus 5t squared plus 3t plus 2. And if you know that, even if you forget the formulas, you can just differentiate v. You can just differentiate x to get v. So it's minus 10t plus 3. And, of course, the acceleration is minus 10. So now, at any time, we know where the ball is, and we also know how fast it's going. Kind of nice, huh? So we can knock off the first 3 parts pretty quickly. For part 1, how long to the ground? Well, when does it hit the ground? What do you know about the particle at the moment when it hits the ground? You don't know how fast it's going. That's part 2. But you know where it is. Where is it? Height 0. So 0 is the ground. So to find out how long to the ground, set x equals 0. And you end up with the quadratic equation minus 5t squared plus 3t plus 2 equals 0. And it turns out that this thing factors into minus 5t and t. And what are we going to get? Well, this would give me minus 5t squared plus 2 minus 2 plus 5. So that means that either t equals 1 or t equals, if you work it out, minus 2/5 is the other option. Bless you. Now, which one is realistic? Property 1. It lands on the ground 1 second after I throw it. Or property 2, it lands on the ground 2/5 of a second before I throw it. Well, it would be kind of cool if I could make it on the ground automatically 2/5 before I throw it. Here we go. 1, 2, oh, well, I can't do it. So this is not realistic. It has to be after I throw it. So it takes 1 second to hit the ground. Okay, so that's part 1. So part 2, how fast does it hit the ground? Well, I know that the velocity at any time is minus 10t plus 3, and I know it hits the ground when t equals 1. So when t equals 1, v equals minus 10 times 1 plus 3, which is minus 7. Okay, how can the velocity be negative? What does that mean? Well, remember, positive is upwards. So if the velocity is negative, it just means it's traveling downward. Well, guess what? When it hits the ground, yes, it's traveling downwards. It doesn't come up through the ground and hit it. Okay, so basically the speed when hitting the ground is 7 meters per second. You can write s or sec, whatever you prefer. And finally, the question is, how high does it go? Well, to solve this question, you need to ask yourself, what actually is the speed or the velocity? What is the velocity at the instant the ball is at the top? Is it going up or is it going down? Well, it's just finished going up, and it's about to go down. So the end result is it doesn't have any velocity. So at top of path, velocity is 0. That's a useful fact. So if you solve this equation, v equals minus 10t plus 3, we find that 0 equals minus 10t plus 3, so t is 3/10. So that means 3/10 of a second after I threw it, it's at the top of its path. But of course, that doesn't tell me how high it goes. So I need to work out how high it is when t equals 3/10. X is equal to minus 5t squared plus 3t plus 2. And I need to actually substitute in 3/10. And there's a bit of fractions to work out, and I believe that you end up with 49/20 meters. So it's actually 2.2 and 9/20 meters. So it doesn't actually go that high. The acceleration just pulls it back. It started at 2 meters above the ground, and the highest it gets is 49/20 meters above the ground. Okay, any questions so far before I move on to the last two parts? Well, let's quickly knock them off. In the last two parts, I have to change the equations because now I've changed the motion. I'm no longer throwing it up, I'm throwing it down. How do I change it, though? The height is still 2. What's the difference? The initial velocity is no longer 3, but I'm throwing it down, so it has to be negative 3. I said I'm still throwing it at 3 meters per second, but now change u to be minus 3 instead of 3, but h is still 2. So the equations lead to x, the position, is minus 5t squared, but instead of plus 3t, it's going to be minus 3t plus 2. And to solve part 4, you need to work out when x is 0, that means it's on the ground, and you solve this again. You have to do another quadratic, and you will find that t is 2/5 this time. So the difference is, I threw it up, it goes down, it takes 1 second. I'm leaving this as an exercise, you just have to factor the quadratic, but you will find if you do it correctly that if you throw it down instead, it reaches a height of 0 after only 2/5 of a second. And for the fifth part, v is now the derivative of x, which is minus 10t minus 3. When t equals 2/5, v is minus 10 times 2/5 minus 3, and if you work that out, you get minus 7. So once again, hits the ground at 7 meters per second. It's negative, of course, because it's going down. So I just want to think about what we just proved. I took this ball, I took it at the height of 2, I threw it up, it went up, it went down, it hit the ground at 7 meters per second. That's the same as if I started and threw it down at the same speed instead of throwing it up. It still hits the ground at 7 meters per second. Is that a surprise? Who's surprised by this? Who's not surprised by this? Who's just totally stunned? We have some people who are stunned. Who is just stunned into, like, insomnia? How about soporific sleep? Who's too stunned to even listen to what I'm saying? Okay, anyway, whatever the case is, you shouldn't actually be surprised, because if you think about it, if I throw it up at 3 meters per second from this height, it goes up, it stops, it comes back down, and actually, when it reaches the starting point, by symmetry, it's gone up, it's gone down. Instead of 3 meters per second up, it's going at 3 meters per second down. And it's just the same as if I threw it down at that speed. So of course it hits the ground at the same speed, it just takes a different amount of time to do it. Right, so that's a nice little example of how to do a motion problem in constant parameters. And that's kind of what I wanted to say about motion. Of course, you'll have other questions, and we can look at those at 9:30, which is approaching pretty quickly. All right. Here's what I'm going to do. I'm going to skip the derivatives of trig functions, which is section 7.2. And then if I have time at the end, there's 3 more types of differentiation problems that I would hope at some point to go over. But if I don't, then c'est la vie. I don't have unlimited time. So I'm going to jump ahead to section 7.2 and spend some time talking about differentiation of trig functions. We did all the limits. I need to do derivatives. Well, I feel like what I say wouldn't be complete without a proof that d dx of sine x is cosine x. I would love to show you this, even though it's standard, and you probably would never have to prove it on a test. So all this talking over here is distracting me a little bit. If you could save it I know you're talking about the math, but I have limited time, and maybe we could wait 20 minutes or so. I'd appreciate it. So anyway, let's let f of x equals sine x. Then f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. It's not inconceivable you could be asked to show this directly, but pretty unlikely, at least in Math 103 at Princeton. This is sine x plus h minus sine x over h. Now, in the very first class, what I did, I showed you that you can bust up the sine as sine x cosine h plus cosine x sine h. And then we still have the sine x. Anyway, if you factor this out, you can write this as 2 limits. So I'm going to group the sine x together. I'm going to get sine x outside of cosine h minus 1 over h. And I'm going to get a cosine x times sine h over h. And now I want to take the limit as h goes to 0. Well, last week I actually proved that the limit of 1 minus cosine h over h is 0. I put a box around it. And we also discussed that the limit of sine h over h is 1 as h goes to 0. The point is that this in the limit is sine x times 0 plus cosine x times 1, and that ends up as cosine x. So there is a proof based on those crucial limits, especially the sine h over h as h goes to 0, that the derivative of sine is cosine. Now, from there, it's easy to get all the other derivatives, since all the trig functions essentially spring from sine. Cosine is just a shift of it. Tan is sine over cosine. Secant is 1 over cosine. You can use the quotient rule, product rule, all the things that you need. The chain rule, you don't really need the chain rule. But you can use the rules to find all the derivative formulas. And the proofs are in section 7.2. But I would like to show you, I would like to state what they are and claim that you simply have to learn them. So here are the 6 derivatives that you absolutely need to learn. The one we just proved. You need to know the derivative of cosine x. Do not forget the minus. It is minus sine x. And the derivative of tan, well, you use the quotient rule, because tan is sine over cosine. And if you work it out, you find that it is secant squared of x. Just how it works out. I didn't make it that way. That's how it comes out. d dx, well, let's just do the derivative of secant x first. Turns out that's secant x times tangent x. That's a very common one. You've got to remember that. Derivative of secant is secant times tan. But the good news is the derivative of cosecant isn't so bad. It's cosecant times cotangent. Right? Secant, tan, cosecant, cotan. There is a price to pay for the co, though. You need a minus. You even see this for cosine, right? The derivative of sine is cosine. The derivative of cosine is co-cosine, which is sine, but you need a minus because of the co. And similarly, the derivative of cotangent x is, well, tan cotangent, secant cosecant squared. But because of the co, you need a minus. Okay, those 6 derivatives, unfortunately, you just need to memorize them. Math doesn't really have much to do with memory. But nevertheless, unless you are lucky enough, and you are not at Princeton, you may be on the net somewhere, but unless you are lucky enough to be provided with a table of derivatives, I'm afraid you're just going to have to pull them out of wherever, your air, your minds, somewhere else. You need to know them. Okay, so learn it. Right, so in some sense, that's actually all there is to say about trig derivatives. But you do need to be able to do things like this. What is d dx of, say, x squared sine x? That's the function we looked at earlier. It's a product of x squared and sine x. And you can't particularly simplify it. You need to use the product rule. You need u equals x squared. V is sine x. So du dx is 2x. dv dx, the derivative of sine, is cosine x. And now you just do the cross multiplication. So this is dy dx, where y happens to be equal to uv. So by the product rule, it's v du dx plus u dv dx. V is sine x times 2x is the derivative of u, plus u x squared times the derivative of v, cosine x. So it's sine x times 2x plus x squared times cosine x. Not so bad. How about this? Let y, and now here's the example that I promised. It's a 3-way chain rule. Okay, let y be equal to sine to the 4th of 5x cubed. What is dy dx? Well, this is a cruel question because I didn't really give you the 3-way chain rule. So now we get to see it. How do you calculate y knowing what x is? The first thing you have to do is you take 5x cubed. Then you take sine of this, and then you take the 4th power. So I'm going to go so far as to rewrite this as sine 5x cubed, all that to the 4th power. So here's what I really want to do. I want to say, let u equal 5x cubed. Then I need another variable. I'll call it t. Let t be sine of u. And finally, I claim that y is t to the 4th. Okay, let's review this. I started with x. The first thing I do is take 5x cubed, that quantity. I'm going to call that u. Then the next thing I have to do is take the sine of that quantity. So that's sine of u. And I'm going to call that t. And then finally, I have to take this quantity t and raise it to the 4th power, and that's what y is. Okay, so it's a chain from x to y through not just u, but also t. Okay, so it's a sort of 3 chain instead of a 2 chain. So here's what the formula looks like. It's pretty much what it has to be. It has to be y depends on t, so it has to be dy dt. T depends on u, so it's dt du. And u depends on x, so it's du dx. And of course it makes sense if you sort of imaginarily think of cancelling. You can't really cancel, but the chain rule says that it actually works as if you could cancel. So dy dx, well, when I change x, u changes a little bit, magnifies by du dx. Then t will change in response and magnify that by dt du. And finally, y will change in response to that. And so it's 3 magnifications. Well, we better come over here and work out what du dx is. It's 15x squared. No problem. What about dt du? Well, we've just seen the derivative of sine is cosine. And how about dy dt? 4t cubed. So if we come over here, dy dt is 4t cubed, dt du is cosine u, and du dx is 15x squared. And that's the derivative. Are we done? No. We were given y as a function of x. And what's all this t crap and u crap? You need to clean up after yourself. Okay, well, I should clean up after that bit of chalk, but I'll do that later. 4t cubed. What is t? T is sine u. So this is sine u all cubed, or just sine cubed u. And I'll leave the rest for the moment. So that got rid of the t. How about the u? Well, u is 5x cubed. So it's 4 sine cubed of quantity, 5x cubed, times cosine of 5x cubed, times 15x squared. And if we want to be nice about it, and we probably should, we can just consolidate the 4 and the 15, and it's nice to write the x squared out the front as well. So we get 60x squared, sine cubed, 5x cubed, cosine, 5x cubed. And that's the derivative. Where's my eraser? Right, are there any questions about trig derivatives? You know, you've got to practice all 6 of them. I just did sine examples, but you've got to make sure you know all of the derivatives, product rule, chain rule, quotient rule. But that's all it really is to derivatives of trig functions. Any questions? Well, I don't have much time left. So what I'd like to do is just finish off by saying a little bit about simple harmonic motion. Now, there is a question first. Oh, absolutely. You don't have to change cosecant to 1 over sine. But if you happen to have, say, sine x times cosecant x, it wouldn't be a bad idea to replace that by 1. But most of the time, it's not. It doesn't simplify very much. Another question? Oh, well, there's at least one example in my book, but I don't remember about the the textbook for the Math 103. But I actually just made that one up on the spot. You can take any trig function, right, raise it to any power, and take it of any polynomial, and you should be able to do it. Okay? You don't realize this, but it's actually easy to make up your own examples for a lot of the course. Not every question, but for things, computation things, just do it. And then if you want to verify your answer and you're at least in the room, you may email me, and I will be very happy to check it for you. Okay? Now, so just in my last few minutes, I'd like to cover a little bit more about motion, because we did spend some time on motion. And so I'd like to talk about 7.2.2, which is simple harmonic motion. Just spend a little bit of time on this, because it's a nice sort of application of this. So I talked about the motion of dropping something down, so constant negative acceleration. But consider a mass on a spring, bounces up and down. Okay, so that's a different sort of motion. This one's not periodic. Bang, it just falls, it hits. Whereas this one is periodic. It repeats itself over and over and over again, just like trig functions. So it turns out that you can model this situation by sines and cosines. So here's the deal. Suppose that the acceleration is equal to minus k, where k is a constant, times your position. Well, what does that mean? Your position 0, and I'm going to take upwards as positive and downwards as negative. So this means if I'm above 0, the acceleration is actually negative. And the further I am above 0, the more negative it is. Right? Because x is bigger, so acceleration is a bigger negative number. But when I'm below 0, x is negative, so the acceleration is actually positive, meaning upwards. So, and the further down I get, the more the acceleration. So I'm going up, but the drag down is more and more and more. And then I go down, and the drag up is more and more. And that is what sets up these oscillations. So if I have such an equation, what then is the solution to it? Well, the problem is this is a differential equation. What do I mean by that? Well, the acceleration is actually the second derivative of x. So if I were to write this out, I get d2x dt squared is minus kx. Ugh. Well, I'm not ready to talk about differential equations. In fact, I won't be ready till the end of Math 104. Although, maybe I'll say a little bit about exponentials when I get up to chapter 9 in the book. But for the moment, let's just look at a simple example which will illustrate what's going on. Suppose x is equal to 3 sine 4t. What does that mean? Well, at time 0, it's at position 0. And then 3 sine 4t is just a standard sine wave. It's compressed by 4 and stretched out by 3. But basically, this thing is going to go up, and it's going to go down, up, down, up, down. It goes to a height of 3 and down to minus 3, because that's what happens to sine 3 sine 4t. So it does look like about the right motion. What I want to do is find its velocity. The velocity is dx dt, and now I know how to differentiate this. Now, I would like you to tell me the derivative of sine 4t. What's the derivative of sine t? Cosine t. So what's the derivative of sine of 4t? Well, you should really use the chain rule, but let's do it in our heads. Sine 4t, the derivative should be cosine 4t. But we need to multiply by the derivative of 4t, which is just 4. So this is 3, because that's a constant, times 4 cosine 4t. And this is a really good rule of thumb that will, I can take an aside and save you a lot about the chain rule by just giving you a simple sort of example. What's the derivative of tan 7x? Well, the derivative of tan x is secant squared x. So this should be secant squared 7x. You just have to multiply by the 7. How about the derivative of secant x over 2? Well, it should be secant tan. But it's secant x over 2, tan x over 2. You just have to multiply by 1/2. So basically, I'm just trying to say you don't really need to use the chain rule when x is just replaced by 3x, or 7x, or 10x, or 1/2 x. You just write down the derivative and then multiply by that factor at the end. So here it is, sine 4t, the derivative is cosine 4t times 4. Of course, we also have the 3 here, and we get 12 cosine 4t. So back in our example, I know what the velocity is at any time. Finally, the acceleration is the derivative of velocity, so I now have to take this and differentiate it. Well, I still have a 12 cosine 4t. Well, the derivative of cosine is minus sine. But I have another factor of 4 that pops out, because I've differentiated again. And altogether then, I get minus 48 sine of 4t. And if you compare this to the original value of x, it's just actually minus 16 times x. So we've actually shown that if x does satisfy this movement up and down in simple harmonic motion, then its acceleration is exactly minus 16 times its position. So I've actually verified this differential equation. Anyway, there's a little bit more to be said about simple harmonic motion, but I don't have any time to do it, so I will refer you to section 7.2.2 of the book. So we find ourselves at least missing a little bit of chapter 6. There are a few little problems I wanted to go through. Maybe I'll have some time next time, but as it happens, at least we have more or less finished up to the end of 7. So until next time, on the videos at least, see you then.